In this video, I'll be showing you how to derive the energy continuity equation from the Friedmann equations. Now, the Friedmann equations are two very important equations in cosmology, and as you can see, they are right here. So we are required to use these two equations to prove this energy continuity equation. Now, I won't be explaining the meaning of the parameters in the equations because I'm assuming that you already know them. We'll just go straight into using the equations. So the very first step is to take this first Friedmann equation, multiply all through by the LCM. The reason we are multiplying all through by the LCM is because we want the equation to be like plain. We want to avoid fractions so that it is easier to manipulate the equation in the upcoming steps. So just looking at the equation, we can see that the LCM is 3a squared. So we are multiplying all through this equation by 3a squared. Let's get to work. So we have a dot on a square plus k on a square. All this multiplied by 3a square is equal to 8 pi g on 3 rho multiplied by 3a square. Looking at the right hand side, obviously 3 goes with 3. And looking at the left hand side, a square will cancel with the a squares at the denominators. So what we'll end up with is 3a dot square plus 3k equal to 8 pi g rho a square. The next step is to differentiate both sides of this equation with respect to t. Take note that the differentiation will be an implicit one. So doing it, we get 3 into a dot is generally a function of t. So differentiating this term implicitly, we get 2 a dot dot. And 3k is a constant, so differentiating it will be 0. Of course, no need to write the 0. Is equals to, on the right hand side, rho and a are both functions of t, and so differentiating them implicitly, of course, we will need to use the product rule. So doing that, we get 8 pi g, which is the constant part, into, now differentiating the two functions, we hold the first function and differentiate the second, plus we hold the first function and differentiate the second. So we have 3 into 2 a dot dot is equal to 8 pi g into a square rho dot plus 2 rho a dot. And we can call this equation 3 because we will be using it in the future. Now our next move is to take this second Friedmann equation and we make the parameter a dot dot the subject. And the reason we are making that parameter the subject is because we want to put the equation in such a form that we'll be able to substitute it back in the equation 3 we just had. So to do that, it is clear we need to multiply both sides of the equation by a. We have a dot dot on a is equal to negative 4 on 3 pi g row plus 3p, and multiplying both sides by a times a times a. So this a cancels with this a, and we have a dot dot is equal to negative 4 on 3 pi a g into rho plus 3p. We now take this and substitute back in the equation 3 we got, where we see the parameter a dot dot. Doing that, we get 3 into 2a dot negative 4 pi ag is equal to 8 pi g into looking at the new equation on the left hand side. Of course, this 3 gets rid of this 3, and this 2 will multiply this 4 to become 8. So we apply those two calculations and we rearrange the equation in a simpler form. We get negative 8 pi a dot g into rho plus 3p equals to 8 pi g into a square rho dot plus 2 rho a dot. Alright, in this simpler form, we see that there are still things that can cancel out, like 8 pi and g, 8 pi and g. So once again, the equation can be brought down into another simpler form as negative a dot into rho plus 3p is equal to a square rho dot plus 2 rho a dot. We can send this term on the left hand side to the right hand side so that we get rid of this negative sign. So we have a square rho dot plus 2 rho a dot plus a dot into rho plus 3p is equal to 0. And as you can see, the equation is slowly starting to be in the form of the energy continuity equation. Now when you compare this equation with the final energy continuity equation we are targeting, you can see some little bit of similarities already there. There is a term in brackets, there is a term in brackets here, there is a rho dot term here, and there is a rho dot term here. Now looking at the term in brackets, we cannot get much hint on how to proceed, but looking at this rho dot term, we can see that it has an a square in it, meanwhile the one here is independent of a square. So obviously, the next hint on how to proceed to make this equation look more like the final equation, we need to divide all through by a square. So dividing all through this equation by a square, we get this on a square, on a square, on a square equal to 0. So this a square cancels this a square. A in this numerator cancels out 1a in the denominator, and a here cancels out 1a in the denominator too. And what we are left with is rho dot plus 2 rho a dot on a, put that in bracket, plus a dot on a into rho plus 3p equal to 0. Okay, now we see that a dot on a dot on a is common here. So we factorize it to make it more simpler, and we get rho dot plus a dot on a into 2 rho plus 3p equal to 0. And looking at the simpler equation now, when you look at the terms in this bracket, you see that 2 rho plus rho is equals to 3 rho. And the equation comes down to rho dot plus a dot on a into 3 rho plus 3p equal to 0. Okay, looking at the bracket again, 3 is a factor which can be factorized out, and again the equation can be expressed as rho dot plus, we bring the 3 outside, 3 a dot on a into, now we are left with rho plus p equal to 0. So looking at this, it's already the energy continuity equation. All we need to do is we send this to the right hand side, and on doing so the sign changes from positive to negative. So we have rho dot is equal to negative 3. Of course, you know, multiplication is commutative, so if you put this term before this term or this term before this one, it's the same thing. So we have rho plus p into a dot on a, and this is the energy continuity equation proven as we have here. So if you enjoyed the video, feel free to like and subscribe. If you didn't understand anything, feel free to drop a comment and I'll do my best to explain. If you want a PDF of the type solution, I'll be leaving that in the description, and also my contacts where you can suggest solutions you wish to see, and also hire me for some difficult problem solving. I really hope the video was helpful. Stay tuned and I'll see you next time. Thank you.